Hello, my name is Benjamin Capps, and today I'm going to be going over material selection for microelectronic heat sinks for ME575. The case study I used was called Material Selection for Microelectronic Heat Sinks, an Application of the Ashby Approach. In this case study, the main focus is finding a material that maximizes the performance of heat sinks. The Ashby method was used to determine the material, and the constraints used for that method were they needed a material that was going to have high electrical resistivity, and there were dimensional constraints as well. The objective was to maximize thermal conductivity so that heat sinks could more easily dissipate the thermal energy produced by things like microprocessors. The different material properties evaluated in this study were thermal conductivity versus electrical resistivity, thermal expansion versus Young's modulus, and thermal contact resistance. One of the major questions that was answered by this study was what materials have both high thermal conductivity and high electrical resistivity. And as you can see on the graph, aluminum nitride, aluminum oxide, and silicon nitride all fit this very well. A material with a high thermal conductivity will be able to dissipate heat more efficiently, and they needed a material that would be high in electrical resistivity as well, considering that a lot of these are used in electronic components. The second big question that this study answered is what material has the maximum Young's modulus and thermal expansion. As you can see on the graph, copper, zinc, and aluminum alloys fit this really well. And the reason why evaluating these properties are important is because whenever materials heat up or cool down, they expand and contract. And if dimensional constraints prevent parts from expanding or contracting, then that can also cause a major problem. To summarize, the three cases that the research paper looked at all concluded that aluminum or aluminum alloys were the best material to maximize the performance of microelectronic heat sinks. My concluding remarks is that the research paper did a very good job of mapping out how they came to conclude that aluminum is the best material for the job.